Hi everyone, welcome to the lecture 15 of this course Classical Mechanics 1. Today we will learn how to construct the Lagrangian for simple system. Before we begin today's lecture, let me recap what we have learned so far regarding Lagrangian. So, recap of last few lectures. So, we have learned the Hamilton's principle. And I said it has two parts. So, part A suggests the introduction of Lagrangian. So, first part says that every mechanical system is characterized by a definite function of generalized coordinate qi, generalized velocity qi dot and t. And second part says that how will be this what will be the structure of this function, that the system, classical system, will evolve in such a way that a mathematical quantity s, which is defined from some initial time to final time integration of this Lagrangian dt, this quantity should be extremum. So, dynamics should be such that this quantity should be extremum. So, second part says that delta S should be 0 for the path in which classical system will evolve. And using this, we obtain the equation of motion for the system. So, this implies that equation of motion, that ddt of del L del qi dot minus del L del qi equal to 0 for I equal to 1 to 3 to 2 degrees of freedom. If you have s degrees of freedom, you have to find s such equation, which is a generally second order differential equation. So, crucial point is the to find. So, to find thus Lagrangian of the system. So, once we can find the Lagrangian of the system, then we can find equation of motion, which is known as Euler-Lagrangian equation. Euler-Lagrange equations, okay, and this Euler-Lagrangian equation you have to solve, and the solution will give you the dynamics of the classical system. That means how each and every coordinates evolve with time. So, main point, actually the half of the work will be done if we can construct the Lagrangian of a system. So, we spend some time on that, and we have found that for a free particle, we have seen for free particle, for a free particle Lagrangian is just kinetic energy of the system. This we have explicitly calculate in previous lectures, and also argue from there that if the particle moves under certain potential and the force acting on it is conservative, then for a conservative system, at least, that Lagrangian can be written as T minus U, where U is the potential energy of the system. And this is the kinetic energy the system. However, I warned in my previous lectures that there is no guiding rule that Lagrangian has to be kinetic energy minus potential energy. We have examples or exception that is not kinetic energy minus potential energy. Only requirement that Lagrangian should produce correct equation of motion. So, this is the requirement. So, what we can do, we can start constructing Lagrangian with kinetic energy minus potential energy, then we find the Euler-Lagrangian equation of motion and we see whether it produces the correct equation motion for the system or not. If it is not, then Lagrangian is not of that form. So, we need to modify it. So, today's class will see how to construct systematically the Lagrangian for simple systems. So, for that we will first example we will consider the Lagrangian for simple pendulum. This is a very simple problem, but try to follow the steps I will be going to write to construct the Lagrangian and follow the same steps for other systems also. So, what is a simple pendulum? Simple pendulum is that some mass point which we call bob, this is stacked with a inextensible string L and it has a motion in this vertical plane. So, it oscillates in this vertical plane. So, we have to find Lagrangian for this system and this is point of support. The string is massless and fixed length of L, and the whole mass point, this is a point particle, whole mass is concentrated here. Okay. So, first you have to choose, first step you have to choose a coordinate system. Appropriate for your problem. So, in this case let us choose the coordinate system as this is my x axis and this is my y axis. Okay. And then in this coordinate frame, this point at any arbitrary time, this mass point is described at given by the coordinate x and y. Okay. So, I can write now okay. Then we have to find the degrees of freedom. So, next step, second step has the you have to find degrees of freedom. So, to find degrees of freedom we need to know the constraint of the system. Okay. So, it is this mass is moving in xy plane. So, this m is moving in xy plane or oscillating in this plane which is attached to a string of length L. Okay. So, it is a one point particle in plane. So, one particle on a plane implies that maximum possible degrees of freedom will be 2 minus the number of constraints, if any. So, we will find that this system has a constant, because if we this length of the string is fixed and we choose this point of support is at 0 0. So, if the point of support as 0 0, then the length of the string is x square plus y square, which is L square. So, this is the constraint equation. constraint equation. This is also we know is a holonomic constant. Okay. So, degrees of freedom. So, second step is the degrees of freedom is 1. So, eventually the Lagrangian will obtain will contain only 1 degrees of freedom, 1 generalized coordinate. Okay. Okay. So, now let us write the what will be. So, we proceed with that. Lagrangian is third step is Lagrangian is t minus u. So, t when a particle in 2 dimension, we can write half m x dot square plus y dot square, and the potential energy, what will be the potential energy? Now, important point is that potential energy you have to say with respect to some point. So, where we will consider the potential energy 0. So, let us assume that this point, this is the potential energy is 0 at this surface. So, if it is positive, if I go up, if it is negative, if we go down. So, potential energy of the system in according to our convention or whatever situation we have assumed will be minus mg y. Why minus? Because I have assumed the potential energy at the point of support. This is my 0 of the potential energy, and the mass is down at length y. Because if we take this, so this will be my x and this will be my y. Okay. And suppose this angle is theta. Theta is appropriate to describe the pendulum motion because in terms of angle of oscillation. So, Lagrangian is supposed to be half m x dot square plus y dot square plus mg y minus potential energy. So, mg y, but we have not incorporated the constraint. So, constraint is x square plus y square equal to s square. So, in terms of angle, we can write the constant, we can write it x and y in terms of a angle theta. So, you will have x equal to L sin theta and y equal to L cos theta. So, if we substitute, then your Lagrangian will be a function of theta and theta dot, what we have expected, because I said that it is only 1 degrees of freedom. So, there should be only 1 generalized coordinate in the system, and that will be now you will see that will be the theta. So, we have to substitute. So, let us do this exercise systematically. So, this x dot will be L is constant, cos theta and theta dot. Y dot will be L sin theta minus sin theta times theta dot. So, x dot square plus y dot square will be L square theta dot square. So, if I substitute the x and y in the Lagrangian, so I will get the Lagrangian which will appropriate to describe the simple pendulum is half m L square theta dot square plus mg, and y is your L cos theta. So, this is the Lagrangian for this system, and you have to check it is consistent with the degrees of freedom and number of generalized coordinate. Okay. So, we follow, let me repeat, we first choose a coordinate system to describe this particular problem, and we define our coordinate axis. Then we find the degrees of freedom. So, you have to find what are the constraint of the system. So, once you find the constraint, you can find subtract that maximum possible degrees of freedom minus the number of constraint. So, you will find the actual degrees of freedom, and once you find the degrees of freedom, you know that your Lagrangian, final Lagrangian will depend on how many generalized coordinate. So, you eliminate the constraints, then you construct the kinetic energy, write a general kinetic energy without considering constant, write the potential energy, and then apply the constraint condition to reduce it to the number of degrees, number of generalized coordinate present in this. Okay. So that way we find that this is the Lagrangian for a simple pendulum. Now we know that equation of motion for a pendulum. So let us find the Euler Lagrange equation for this system. Okay. So if we find the dt of del L, del theta will be ml square theta dot minus del L, so is mg L minus sin theta will be equal to 0. So this implies m L square theta double dot plus mg L sin theta equal to 0. So this will be the equation of motion. So let me simplify this little bit. Theta dot plus mf get cancelled, so g by L sin theta equal to 0. So this is the equation of motion for simple pendulum. And we know it will have a simple harmonic oscillatory motion if for a small angle. So for small angle and in radian measure, sin theta can be approximated as theta, and you can have a harmonic oscillator equation of motion where omega is root g by L. So frequency of oscillation is omega, which is nothing by g by L. So this is fine. So we have found that the Lagrangian for a simple pendulum, and we have found that it produces correct equation of motion, and you know one can find a solution. Ultimately one has to find solution. So solution can be written, you know, solution for this at variable this the angle of oscillation, how it changes with time will be a sin omega t plus b cos omega t, or alternatively you can write a cos omega t plus delta, because it is a second order differential equation. So two unknown constant will be there, and in the first solution it is a and b, and second solution you can have these unknown constraints can be fixed from the initial conditions. Now I consider, so this is all about the simple pendulum. So now let us move to a more complicated system. As I promised, today lecture will be mostly on various type of pendulum. So second example we consider, so example 2, a double pendulum. Okay. So a double pendulum, let me draw how looks like. So double pendulum, again it is this is point of support, and its some mass is attached to this, and then you have that another pendulum is attached to the first pendulum. So let us write this is L1 and this mass is M1, this string is L2 and this is M2, and this is fixed. Again all these things are same, that lengths are fixed and the strings are massless, the mass points are point particles. So what will be the Lagrangian for such system? Again we follow the same procedure as I discussed. So first define our coordinates, or what will be the axis. So let us consider this is our x axis, and we consider this is our y axis. And we all know that for a pendulum problem it is always convenient to describe the motion in terms of angle of oscillation, so let us consider that two angle of oscillation as theta 1 for the first pendulum and theta 2 for the second pendulum. So first we have assume our coordinate axis, and any arbitrary time m1 point is at x1 y1 and m2 mass will be at x2 y2. So next problem is that, so coordinate axis, so coordinate axis, then second is the degrees of freedom and constraints. So two particle, so we have two particles motion on a plane. So maximum possible degrees of freedom equal to 2 into 2, 4. And now we have to find number of constant. So because we have two fixed length L1 and L2, we will see that we will have two holonomic constant. So constant is that distance between, so the point of support is at 0 0, we have chosen. So this will be at 0 0, and now the distance between the point of support to the first mass will be x1 square plus y1 square equal to L1 square. So this is a constant, first constant. Similarly, distance between the first mass to the second mass also will be constant. So x2 minus x1 whole square plus y1 or y2 minus y1 whole square will be L2 square. So two constant, two holonomic, and they are independent constraints. So the degrees of freedom, so actual degrees of freedom for the double pendulum, so degrees of freedom will be 4 minus 2 will be 2. So whatever Lagrangian we find at the end will have only 2 degrees of freedom, and we can see very naturally that this will be theta 1, theta 2 and theta 1 dot, theta 2 dot. It will be the structure of the final Lagrangian. But now how we will find this Lagrangian? So let us do this. Lagrangian will be kinetic energy of the first particle, kinetic energy of the second particle minus potential energy of the first particle minus potential energy of the second particle. So this is kinetic energy of m1, this is kinetic energy of m2, this is potential energy of m1, this is potential energy of m2. Okay. So now, so naturally from the earlier example you can find that it is half m1 x1 dot square plus y1 dot square, T2 will be half m2 x2 dot square plus y2 dot square, and u1, if we consider the same 0 of the potential energy, I will just, after finishing this, I will explain that if we choose potential energy in a different place, 0 of the potential energy in a different place, then you have the same equation of motion. Lagrangian will change, but equation of motion will be same. Lagrangian may change by a constant amount. So this will be m1g y1 and minus, because we are considering the zeros of the potential energy. So Pe is 0 here. So if we go up, it will be positive. If we go down, so negative potential energy. So u1 is minus m1g y1 and u2 will be minus m2 y g1. Now in this point, let us consider that we have the zeros of the potential Okay, so that will comment later. So if you have the zeros of the potential energy somewhere else, then basically the potential energy of that particular reference frame, difference between the zero of this, you have to add to the Lagrangian, which is a constant quantity. So Lagrangian will not be affected. Okay. So now if I write the Lagrangian in terms of these T1, T2 and U1, U2, so its Lagrangian seems to be function of x1, y1, x2, y2, x1 dot, y1 dot, x2 dot and y2 dot. So it is 4 variables, but as I said, the number of degrees of freedom are 2, so your Lagrangian should depend only on two of them. So basically you have to eliminate this x and x1, y1, x2, y2 in terms of theta 1 and theta 2. For pendulum, earlier simple pendulum problem, you know how to replace this. So x1 should be L1 sine theta 1, y1 will be L1 cos theta 1, and x2 minus x1 will be L2 sine theta 1, that is x2 will be x1 plus L2 sine theta 2, and if I substitute x1 again, so L1 sine theta 1 plus L2 sine theta 2, this will be your x2. Similarly, if I calculate y2 will be y1 plus L2 cos theta 2, but y1 is L1 cos theta 1 plus L2 cos theta 2. So this is your y2. So now you have to do little bit of algebra. That algebra is x1 dot will be L1 sine cos theta 1 dot. Similarly, y1 dot will be L1 minus sine theta 1 dot. x2 dot will be L1 cos theta 1 dot plus L2 cos theta 2 dot, and y2 will be L1 minus sine theta 1 dot minus L2 sine theta 2 dot. So all this you have to substitute in the Lagrangian, and you will find, let me write final form of this Lagrangian, and then we will stop this class because of time. So after substituting all this simple algebra, you will get theta 1 theta 2 theta 1 dot theta 2 dot as half m1 plus m2 L1 square theta 1 dot square plus half m2 L2 square theta 2 dot square plus 2 L1 L2 cos theta 1 minus theta 2 theta 1 dot theta 2 dot plus 2 m1 g L1 cos theta 1 plus m2 g L2 cos theta 2. So this will be the full Lagrangian, and you can see that this is complicated in that compared to the first case of simple. So maybe because of time I will stop here in this class, and then we will continue with this problem in the next class. Okay, thank you.